Right, so I'm Ron Pressler, I'm based in London, and I work at Oracle in the Java platform group. That is the group that develops OpenJDK, the main implementation of the Java platform. And that's where I lead a project called Project Loom, whose mandate is to make it easier to develop scalable concurrent applications. The way we've decided to do it is by letting the programmer, when they create a Java thread, choose if they want it to be backed by an OS thread or be a user mode thread. We call them virtual threads, and a single VM can support millions of virtual threads. I should note that Project Loom isn't done yet, so I'm talking about a future feature of Java. But this isn't a Java talk, and I won't get into the details of our design. I've done that elsewhere. Rather, this is a brand new talk I prepared specifically for CodeMesh that explains the reasoning behind our general chosen approach. This approach is similar to the one taken by Erlang and Go, but different from other languages like C#, JavaScript, Kotlin, and C++ and Rust that attempt to support scalable concurrency with a new syntactic construct that I call syntactic coroutines, but is mostly familiar to us as async await. So that's how I'm going to call it. In this talk, I'll try to explain why we've decided that user mode threads are the preferable path for Java and why those other languages chose differently. We'll be talking about concurrency, but what that means exactly depends on how we frame it. And that perspective can actually influence the solutions we pick because we end up with somewhat different emphases. In particular, we'll be looking at concurrency from a semantic and a syntactic perspective. Let me explain what I mean by that. The semantic perspective looks at the algorithm, what it is that we're trying to do. And we could talk about concurrency that way. The syntactic perspective looks at how we express what we want to do in a language, and concurrency can also be described in that way, and the two definitions aren't equivalent. From the algorithmic perspective, concurrency is the algorithmic problem of scheduling or assigning largely independent tasks to computational resources. By computational resources, I mean processing cores and I/O devices, and usually their cardinality is much smaller than the number of tasks. In terms of performance, what interests us is the throughput, and we'll talk much more about that later. Now, it's helpful to contrast this, concurrency, with the algorithmic problem of parallelism, where we have just one task, and we want to make the latency of performing it faster, shorter, by splitting it into cooperating subtasks so that we can exploit multiple processing units. But if we look at concurrency from the perspective of how we express our programs in a programming language, rather than the problem we want to solve, the distinction between the two is less clear. From the syntactic perspective, concurrency is the problem of how to express some arbitrary combination of sequential and parallel compositions, where a sequential composition means that something must be done after another as it depends on it, while a parallel composition means that we do two things at the same time. I'll only be talking about imperative languages or imperative subsets of languages, because this is where this distinction matters. Or conversely, I will define imperative languages as languages where this matters. So we have a sequential composition operator that in our chosen languages, concrete syntax can take multiple forms, like this or that, etc. A parallel composition operator, we can support a join operator, a join operation, rather, it's not a distinct operator, that sequences something after a parallel composition, as well as some atomic operations such as, or primitive operations such as assignment to variables, I/O, and some means to share data and coordinate work like channels and locks. And this would be an example of concurrency from the syntactic perspective. Look, something, just writing something like this. Now, applications have some natural units of concurrency. That's one of those largely independent tasks. For example, in a server, this can be a single transaction. We organize our code according to this natural unit, but just as importantly, this unit defines a context of an operation that's used in troubleshooting, where, say, we want to trace the execution of one of these units in the debugger, and in profiling, where we want to know where each unit spends its time. So we want our solution to address all these important aspects. And for the purpose of this talk, I will call such a unit a process. Now, let's define it more precisely. Syntactically, a process is some sequential composition of operations. Each of those can be primitive or complex. And we see that a sequential composition of processes is also a process. Semantically, a process can be viewed as a state machine, not necessarily a finite state machine, with some initial states and some final states. And of course, chaining multiple state machines also gives you a state machine. Perhaps I should also note that the parallel composition of two processes is also a state machine, but those will have different states. It's going to be a cross product of the two processes, but we won't be getting much into that. If you look at these transitions here, you'll see that this state machine has some non-determinism. We can go from this state to either this or that. And that's because we can do I/O, like read input from the user and choose our next state according to that. If you're interested in this particular aspect, you can see my talk on non-determinism in programming languages and the relationship to our subject. But now I want to talk about a kind of process that's very common in programming languages today, and that's a thread. I'll define it as being what we normally associate with threads in our programming languages, namely a process with a call stack. We see that each subroutine is itself a process or a state machine. When we return to a caller, we land at a state that's some composition of the subroutines of the caller's current state as well as the return value, if any, from the callee. And this combination of individual processes is the process construct that we call a thread. Now, what does it mean to implement threads? It means implementing a scheduler. That's a process that decides when and how to assign the threads to processes, and it means verifying the state of the thread in some data structure that allows scheduling the threads by suspending and resuming them. What does that data structure look like? Well, it's a stack that represents a state of each of the subroutines. And each of those substates that contains the subroutine's local data as well as a program counter, which instruction we run inside that subroutine, is called a frame. The operating system provides us with one implementation of threads, but there's good reason to implement them in user mode. Why? We'll get into that later. Some programming languages have a different syntactic construct called async await. I'll assume you know how it works. If not, you can look it up. I don't have the time to get into that exactly. If we look at the semantics of async await, we see that we get the exact same picture as we do for threads. But this construct is completely distinct from threads. And ordinary subroutines and these code units, they're called syntactic stackless coroutines, can only be mixed with subroutines in very specific ways if we want them to work as expected. To use this construct, we need a duplicate set of APIs for I/O and synchronization constructs that do the exact same thing as the APIs for threads, but the two live in a syntactically separate world. So the question is, why would we even consider a distinct syntactic construct to express the same semantic idea as a construct that most languages already have? Well, there are some differences, both in semantics as well as in the implementation, and we'll focus on them in the rest of the talk. The first difference we look at is a semantic difference. Threads and async await have different defaults regarding scheduling points. Those are the points in the code where the scheduler is allowed to suspend a process from running on a processor and schedule another, interleaving the two. For threads, the scheduler is allowed, it doesn't have to, but it's allowed, to interleave another thread anywhere except where explicitly forbidden with a critical section that we can express as, say, a lock. With async await, such interleaving can happen nowhere except where explicitly allowed with await. Personally, I think that the former is a better default because correctness of concurrent code depends on assumptions around atomicity. And the first option allows code to say, this block must be atomic, regardless of other subroutines I'm going to call inside it. And the latter is the opposite, changing a code unit from a subroutine to an async coroutine in order to allow it to block. An interleave can affect assumptions made up the call stack. So it can break, so making a change somewhere in the code can break assumptions made elsewhere. But regardless of your personal preference, many languages already have threads. So scheduling points can happen anywhere, anyway. And adding yet another construct with very similar semantics, but slightly different rules only complicates matters. But some languages don't have threads, or rather they have just one thread, and there's no interleaving. For example, JavaScript. JavaScript has just one thread, and all existing code has been written under the assumption that scheduling points happen nowhere. So when JavaScript added a built-in convenient syntactic construct for concurrency, they naturally preferred a model where atomicity is the default. So this is why async await makes more sense than threads in JavaScript. The second difference is in the implementation. If we want to implement threads in user mode, doing so requires redefining the state of the thread, which means representing the state of each subroutine. To do it efficiently requires integrating with a representation of ordinary subroutine stack frames, which usually requires access to the compiler's backend, as that is a very low-level implementation detail. On the other hand, async await is a completely new construct. All that's required for an efficient implementation is control over the compiler's front end. That compile one of those units not to a subroutine, but to something else. Maybe several interrelated subroutines, or maybe even compiling multiple units into a single subroutine with various jumps inside. So some languages don't have control over the backend and access to the low-level representation of subroutine frames, so they simply have no choice. To get an efficient implementation, they must use async await, despite its considerable shortcomings. For example, Kotlin. Kotlin compiles to Java bytecode, and the Kotlin compiler is a front end to the Java virtual machine. But it has no control over the design of the Java virtual machine, which is the backend, and cannot access the required internals. Kotlin also compiles to JavaScript and Android, two other backends it doesn't control, which is why async await makes sense for Kotlin. By the way, this is also a bit of an issue for Rust, which runs on top of LLVM and WebAssembly, but the situation there is a little different. Another difference is in allowing constructs that can result in a non-deterministic stack depth, like recursion and virtual dispatch. And those are two things that subroutines commonly do. This means that thread stacks either need to be very large, that's how the OS does it, but that's a big reason why we don't want to use OS threads in the first place. We'll get to that soon. Or they need to be dynamically resizable. And that has implications on the implementation languages like C++ and Rust. On the other hand, async await is a new construct with, it's a different syntactic thing, and we can say that those two things are excluded inside it. So what's the issue with resizable stacks? First, they require dynamic memory allocation. And while Java has a tracing garbage collector that makes allocations transparent to user code, low-level languages require user code to be aware of allocations so that they can be carefully freed. So this makes things a little more complicated for them. Second, there's the issue of memory allocation deallocation efficiency. Now, Java generally tries to optimize not for worst case performance, but for best amortized performance, or even best average performance. And the OpenJDK JVM, called Hotspot, is full of these common fast paths and rare slow paths. For example, the compiler doesn't need to prove some optimization is always valid. If, say, 1,000 times only one branch of an if-else is taken, the compiler can guess and only compile one branch and insert a trap that would cause a seg fault if the other branch is attempted, in which case we de-optimize and fall back to interpreted code and a slow path. So this is very efficient in the common fast path, but occasionally this will fall to a slow path. On the common path, allocation is just a pointer pump in Java. So it's very cheap. Now, it's true that the same is true for native allocators as well, but I'm trying to simplify matters and just give a simple example. So resizable stacks can impact the cost of context switching from one process to another. Finally, resizing stacks means moving memory containing stack frames around. And that could be a problem if you have pointers pointing into them. Java simply doesn't have pointers into the stack. So this can be done very efficiently. But low-level languages often do have pointers into the stack. And this makes things more complicated as you have to go and fix them. And a related issue is that even if you know where these pointers are for your own language, you don't know them for FFI frames, as those are written in different languages. In Java, FFI calls their do I/O, and I/O is where we want to suspend a thread and schedule another. So that's where we need to represent the stack in some data structure. Those calls are extremely rare. So we can say, well, if you're doing I/O in some FFI subroutine, you can't deschedule the user mode thread, and this will hardly ever have an effect on anyone. But this is not the case in languages that do a lot of FFI. FFI calls can be common in those languages in subroutines, but async await makes it easier to disallow them in coroutines because that's a separate syntactic structure. So the performance impact of resizable stacks that are needed for user mode threads, certainly when we take into account the general performance philosophy of different languages and runtimes, is lower in Java than in low-level languages. But let's dive in a bit more into these performance considerations and also see why resizable stacks are so crucial. To talk about performance, we'll need some definitions. First, latency is how long it takes to do something. Throughput is how many things we can do in a unit of time. Sometimes throughput is just 1 over latency, but many times it isn't. For example, if you want to ship data from London to San Francisco, and you do it by putting it on hard drives and sending them by jumbo jet, you have terrible latency compared to an internet connection, but actually pretty good throughput. Now, to judge how important something is for performance, I'll define impact as the change in performance, either latency or throughput, depending on what we care about, when we fully optimize its cost to 0. You may recall that I said in the beginning that the syntactic and algorithmic perspective of concurrency can give us different views on what concurrency is. For example, suppose we have to update many game entities every frame. We want to simulate them. From an algorithmic point of view, it's more parallelism than concurrency. But syntactically, we might choose to represent each of those entities as a process. Another example is generators, as used in Python. It's a way to more easily write iterators by representing the iterator as a process that yields one value at a time to the consumer and is rescheduled when the consumer asks for another one. This isn't our definition of concurrency from the algorithmic perspective. We don't have many independent tasks competing for resources, but exactly 2 performing a very particular dance. Still, we could choose to use the same syntactic construct we use for concurrency. And while in practice, we'd normally make direct use of coroutines, the consumer also serving as the scheduler. We can also think of it as two processes, consumer and producer, in a parallel composition, communicating over an unbuffered channel. So I mentioned before that using dynamic stacks might affect the efficiency of context switching, although the magnitude of the effect depends on the particular language, and in Java, it's small. But suppose we're talking about a language where it's large, maybe C++. Let's try to understand the total impact of context switching on the generator use case. We mostly care about the latency of the total traversal time over the data, because we're iterating with generators, we're iterating over some data. So if we take the processing time by the consumer and the producer to be 0, say that all they do is some trivial computation, just increment number and give it back, then context switch is 100% of the total time. So its impact is 100%. How fast can we make it? So we notice that in this case, we only have 2 processes, and exactly 2. And both of their states can fit in the lowest level cache. So switching from one to the other can be just changing a pointer in a register to point to one address and then another. And in fact, we can do even better than that. A good optimizing compiler can optimize the 2 processes away, essentially producing the state machine cross product and keeping all data in registers. And that's because the relationship between the producer and the consumer is monomorphic. In the producer, you often know exactly, in the consumer, you often know exactly who your producer is. So employing the mechanism of resizable stacks for this use case can be unhelpful. However, let's now look at our original use case of concurrency, where we have many mostly independent tasks competing over a few computational resources. And here, the metric we're interested in is throughput. And the throughput of a server processing transactions is governed by Little's law, which is this formula. Now, it looks very simple, but it's not so obvious because it's independent of the, it turns out to be independent of the distribution of the arrival of requests. Little's law applies when the system is stable. It means that the requests don't just pile up in a growing queue. So W is the average latency of serving a single request. Lambda is the average rate of request arrival, but because the system is stable, this is also the rate at which they are dispatched. So in other words, lambda is exactly our throughput. L is the number of requests that are currently in flight being processed, and we'll call L our level of concurrency. So lambda is our throughput, and that is what we're trying to optimize. We can increase it by reducing the latency, W, but we often don't have too much control over the latency. Our server might rely on other microservices or a database, and there's some real amount of work to be done, some minimal amount that we have to do. So to increase the throughput, the easiest thing is to increase L, our level of concurrency. So the biggest impact on the performance of concurrent applications is the number of processes they can handle simultaneously. I'll say that again. The biggest impact on the performance of concurrent applications is not context switching costs. It is the number of processes they can handle simultaneously. Of course, at some level, we start hitting other bottlenecks. And that is why, if we want to represent processes as threads, we must have resizable stacks so that we could have many of them. The OS can't do that because it must support all languages, and it doesn't know how they use the stack. On the other hand, our language runtimes knows our particular language and how it uses the stack. True, the OS can benefit from virtual memory, where it can allocate some portion of the stack in virtual memory, not committed to physical RAM. But A, once a page is committed, it stays committed. And B, the granularity of virtual memory is a page, which is usually at least 4 kilobytes. And even that is far too much if the number of threads are decisive factors. We could want many millions of these processes. So this is where the power of user mode threads over kernel threads comes from. So what about the impact of of the cost of task switching. It turns out that if T is the average latency of context switch, and mu is the average latency a thread waits blocked for some IO or a message from another process, then the impact of context switch and total throughput is T over mu. If you want to see the details of this calculation, look in the slides at this blog post. It shows you exactly how they're derived. i.e., if the average wait time for I/O is 4 microseconds, which is about the fastest latency for an I/O device we have now, then even if the context switch is 200 nanoseconds, as opposed to 0, when we said before, reducing it to absolute 0 would only buy us a 5% improvement in performance, compared to 100% in the generator's case. Moreover, we're now dealing with many processes. There aren't particularly great compiler optimizations available for that case. The call site is polymorphic, and they can't all fit in the cache. So the most efficient context switch in the world would take us at least 60 nanoseconds, as we'll have at least a cache miss. Even if we do nothing, if we just change a pointer stored in a register, we'll get that cache miss. So the fastest context switch in this use case, where we have many processors, more than 2, or 20, or however many fit in the cache, is 60 nanoseconds. That's the best we could possibly hope for. And as long as we're under 200 nanoseconds, our impact is quite small. So even if we're using a language where resizable stacks do have a non-negligible impact on context switching, this might not be worth it to give up on user mode threads. So the point is that even if dynamic stacks negatively affect context switching costs in some language, their impact heavily depends on the use case you try to focus on. If it's generators, then it could be big. But if you mostly care about transaction processing, which normally involves I/O somewhere in the process, then the impact is going to be very low. Going from an implementation that gives you a context switch in 200 nanoseconds to a perfect one that can give you a context switch in 60 nanoseconds will only improve your performance by 3.5%. And that is if your average I/O takes 4 microseconds. If your average I/O is more than 4 microseconds, then the gain in performance from going from this imperfect implementation to a perfect implementation is it going to be even less than that. So 3.5% is best case scenario that you can win. And at which point we should ask ourselves, do we want to duplicate all of our APIs at a scheduling model with completely different default than threads and worse defaults, and in a language where we already have threads for that? That's a very high price to pay for little gain. So in conclusion, if you have control over the backend, if I/O in FFI is rare, if you have no internal pointers, if allocation is efficient and transparent, and if threads are already pervasive in the platform, and certainly if your focus isn't generators, then the decision to prefer user mode threads over async await becomes pretty obvious. And that's the case in Java. In fact, in Java, you don't need to rebuild library binaries that use threads in order for them to use user mode threads. You just use the compiled binaries. Well, but that's because in OpenJDK, the real complication is done just in time. So if we look at the choices some other languages made, we have Erlang, Go, and Java. They've chosen user mode threads, and we have JavaScript, Kotlin, and C++ Rust that have chosen async await. Now, the only language that could have been in the user mode thread camp but isn't is C#, and that's incidentally the language that pioneered async await. Now, I don't have a good explanation for that, except that implementing async await is much easier. And I think this was a mistake on C#'s behalf. Lastly, I want to mention Zig, and that's a new and extraordinary low-level language that deviates significantly from the C++ Rust design tradition. And it's one of the most original and promising languages I've seen in a very long time. And it does something in between. It has the keywords async and await, but they mean something different from async await. And while they don't have exactly user mode threads, they have they don't have coroutines as a distinct syntactic category either. They just have subroutines that you can choose to compile so that they store their frames or their state in two different ways. And with that, I am done, and I'm happy to take questions if there are any.
All right, thank you, Ron. There's no questions quite yet. If you have any questions, please put them up in the WOVA QA for this session. I'll go ahead and start off with one. In Project Loom, is it possible to have both user mode threads and system threads in the same program at the same time? And if so, how do you choose where those boundaries are?
Absolutely. You could choose on a per thread or per task basis if you want to be an OS thread or a user mode thread. In fact, for user mode thread, you can provide your own scheduler in Java. It's completely pluggable. I don't think I've seen it in other languages, and there are no boundaries. Other than you can pick on a per task basis. An OS thread and a user mode thread, for example, can synchronize on the same lock. Then it becomes a completely transparent implementation detail. And in fact, all the existing APIs in the JDK work unchanged. They just don't block any kernel threads. They just block user mode threads.
Wow, that's really interesting. That must be a lot of work to get that all working together.
Yes.
We do have a.
We're not done yet.
we do have a question here from Daniel Craig. I will unmute you.
Can you hear me?
Yes.
Okay, great. So at the beginning of your talk, you mentioned that the contents of your talk mostly only had to do with procedural languages, but I didn't quite catch, or I didn't understand why that was the case. Could you explain that?
Yeah, so I didn't say procedural, I said imperative. Well, and I defined imperative as languages where the order of operation matters. So if you're in a language where the order of operations doesn't matter, which could be the case in Haskell if you don't use, I don't know, the IO type, then the notion of sequential composition disappears. So the distinction between sequential and parallel composition is not that important because there is no notion of doing something after another. These are just pure computations.
Okay, thanks.
I see Mary's raising a hand.
Yes, that's correct. So thanks for your talk, Ron. My question, it's about reactive technology, reactive computing, right? So I've heard of people saying that when Project Loom is going to be their virtual threads, it probably will wipe out reactive technology. Can you comment on that? You know, are they solving the same, problem in the same layer? And
I think it depends on exactly what people mean by reactive. If they mean the actual reactive style, where you use this monadic composition, you chain callbacks, then only the people who truly enjoy programming that will continue using that. So it depends on how many people actually enjoy that. I think it's quite a few, it's rather few people, very few people who actually enjoy that because you lose the context for your stack traces. It's very hard to debug in the debugger, etc. And much of it is going to become unnecessary. However, if by reactive you mean a general tradition or practice of writing scalable concurrent applications, then I do think that there's certainly room for third-party, higher-level libraries above the JDK that can make doing that easier, but above Loom. But I don't think they're going to look exactly as the reactive frameworks today.